Welcome to today's talk. Our subject for today is an introduction to integrated circuit device cross-sections. The talk outline today will start with bipolar transistors. I'll cover vertical NPN devices and lateral PNP devices. Then I'll move on to CMOS cross-sections. We'll look at both a PMOS device and an NMOS device. Next, we'll look at DMOS, then JFETs. Then we'll move to resistors, and there are several different types of resistors. We'll look at diffused, poly, and thin film resistors. The next subject would be diodes. We'll look at PN diodes, Zener diodes, and Schottky diodes. And we'll move to capacitors, and we'll look at MIM capacitors and finger capacitors. And we'll finish up the talk today looking at inductors.
I'd like to start with the vertical NPN bipolar transistor. Here we have a cross-section of a typical NPN transistor. And I know this is a very busy drawing, and I'll do my best to talk about the various regions, point them out, and discuss their purpose. First thing I want to talk about is the color coding. I've color-coded all the P regions with a reddish color, and all the N regions with a blue color. The P regions are doped with boron in general, and boron is an acceptor atom. And I'll talk more about acceptors and donors on the next slide. The N regions are mostly doped with phosphorus atoms, and phosphorus is a donor, a dopant. However, there are two exceptions to the phosphorus doping. That's the buried layer, which is the blue region at the lower middle of the drawing, and the N+ emitter at the upper region of the drawing. Both of these regions, they often use arsenic or antimony to dope emitters and buried layers. And the reason for that is arsenic and antimony are larger and heavier than phosphorus, and they diffuse slower. And when we get to the lecture on semiconductor processing, you'll see why you might want the emitter and the buried layer to diffuse slower than the rest of the N doping that you're putting in. Now I'd like to talk about the sinker and buried layer regions. If we look at the top contacts, one of them is labeled collector. And just under the collector we have an N+ region, and then we have a region labeled N+ sinker with a little resistor element drawn there. And that N+ sinker region connects at its bottom to an N+ buried layer region, where I also have another little resistive element drawn in. The purpose of the N+ sinker and the N+ buried layer regions is to lower the collector resistance of the transistor. So carriers that are being collected in the collector will have a way to get to the surface through a fairly high dope region, meaning the buried layer and N+ sinker combined. So that will give you a more efficient transistor with lower collector resistance. Often you won't see processes with a sinker region. It costs a lot to add an extra diffusion, and a lot of times it's determined that the sinker is not worth the extra money to have it in the process. But some processes have it, so I wanted to show you what a sinker looked like. The buried layer also serves another subtle purpose. It will kill the vertical PNP. It's a substrate PNP formed between the P base region, the N collector region, and the P substrate region. And by putting that buried layer underneath the P base region, that gives you a high dope base region for that vertical substrate PNP, and that pretty much kills its beta. So I haven't indicated that in the drawing here anywhere, but just to be aware that putting the buried layer serves sort of two purposes. One, the main purpose is to reduce the collector resistance. And then also it helps to kill the vertical unwanted parasitic substrate PNP transistor. Now I'd like to talk about the isolation regions at the far left and far right of the drawing. We're looking at a single bipolar transistor here, and all the blue region in the middle is pretty much the collector region. But we have the collector of the adjacent transistor on the left and the right, and those are the blue regions at the far left and far right of the drawing. If we look at the right side, we have a region labeled P plus ISO that's interposing between the collector of the transistor in the middle and the collector of the transistor on the right side, not shown, it's sort of off the drawing. And we've shown a couple of diodes there, and those diodes act as electrical isolation between the one collector and the other collector. Now, it's not an insulator. This is called junction isolation, and what we're doing is we're using reverse bias diodes to isolate one region from an adjacent region, as opposed to trying to put an insulator in there. Generally, in this case, the P plus ISO would be tied to ground, so that substrate would be grounded, and that, or the most negative voltage on the chip. So those diodes would normally be reverse biased. Now all the metal contacts come in at the surface here, and you might notice that underneath every opening where we would put metal, we have a high doped region, either P plus, which means high doped P, or N plus, which means high doped N. And those high doped regions are put in there to form an ohmic contact between the metal and the diffusion. We don't want to form any type of Schottky diode or anything like that here. We want ohmic contacts, very low resistance, nice contacts. And to get that, we want to put high doping in all the regions where metal is making contact with the silicon surface. The NPN transistor action itself is going to occur predominantly under the emitter, and I've drawn in a vertical NPN transistor symbol just under the emitter region here. And you can see it's going to be formed by the N plus emitter, the P plus base, and the N minus or lightly doped collector. In reality, even though I've drawn the base region as fairly large in the vertical direction, it would actually be very small or very narrow in the vertical direction. There wouldn't be much room between the N plus emitter and the N minus collector, just a very thin layer of base in there. And that base region is typically fairly lightly doped, not quite as light as the collector region, but fairly lightly doped, much lighter than the emitter region. So the combination of the lightly doped region, the base region, and it being very thin allows carriers to get across from the collector to the emitter fairly easily without recombining inside the base region. Any type of recombination that occurs in the base is going to show up as base current coming out the base contact, and we'd like to avoid that. So what we are looking for is trying to get high current gain, and current gain of the bipolar is called beta, and beta is defined as the ratio of the collector current to the base current. So the more collector current we get for the less base current, the better. And again, base current is predominantly caused by recombination in the base region. I wanted to go over the periodic table of the elements to show where acceptor dopants lie on the table and where donor dopants lie on the table. But first, let's go ahead and locate where silicon is on the table. Silicon is number 14 on the table, which is sort of on the right side in the third row down. Silicon has 4 valence electrons, and it's located in column 4A of the periodic table. And you may recall from your high school chemistry that the magic number of electrons in the outer shell that's stable is 8. That's the noble gases all have 8 electrons, so they're hard combined with anything. Well, silicon has 4, and the column immediately to the left of silicon would have 3, and that would be column made up of boron, aluminum, gallium, indium, and thallium. Those are called the acceptor dopants, or p dopants. And by having 3 electrons, that means they have 1 fewer electron or 1 fewer negative charge. That's why it's called a positive dopant. The column immediately to the right of silicon, that's column 5 on the periodic table, is made up of nitrogen, phosphorus, arsenic, antimony, and bismuth. Those are called the donor dopants, and they have 1 extra electron or 1 extra negative charge, so they're often called N dopants. One thing I want to mention is a gallium arsenide specifically. Gallium arsenide is one of the many alternative semiconductors that are used to build devices aside from silicon. And if we look at where gallium and arsenic are located on the table, gallium is 31 on the table and arsenic is 33 on the table. And you can see that one of those is coming from the acceptor column and one of those is coming from the donor column. So gallium has 3 valence electrons and arsenic has 5 valence electrons. When you combine them together, you end up averaging 4 valence electrons, which is exactly the same number that silicon has. One of the advantages of gallium arsenide over silicon is gallium arsenide has a much higher electron mobility, and that's very good for RF devices. So you'll often see gallium arsenide used to build high-frequency RF circuitry. The P or hole mobility is not so good in gallium arsenide, so you don't really see any P devices being used in gallium arsenide, just N-type devices that use electron mobility. Just FYI, you may have heard of the gallium arsenide company named Triquint. This is just an interesting fact I came upon. The name Triquint actually comes from 3 or tri in Greek and 5 or quint in Latin, and that's 3, 5, which represent the columns on the periodic table for gallium and arsenic. The next device I'd like to talk about is the lateral PNP bipolar transistor. And here we see a cross-section of what that would look like. Now, lateral PNP transistors are commonly used to save masking steps. Now, because they can be constructed using the same diffusions as a vertical NPN transistor. Really what you'd like is you'd like a vertical NPN and a vertical PNP. But for cost reasons, sometimes you don't want to pay the extra money to have a vertical PNP. So you can create a lateral PNP, meaning sideways PNP, from the same diffusions you've created your vertical NPN with. Let's talk about how this is done. Well, first let's look at where the collector region is in this drawing. You can see the contacts are labeled base, emitter, and collector, and we have basically a collector ring surrounding the emitter. And that collector ring is made up of a P plus region at the top, and that's for good ohmic contact, as we talked about on the vertical NPN, and a P base region underneath. And this would be the P base region is, I'm calling it P base, it's the P base of the vertical NPN transistor, but it's the P collector region of the lateral PNP transistor. The emitter is formed the same way the collector is formed, with a P plus region on top and a P base region underneath. So you can see I've drawn in the lateral PNP transistors schematically in the drawing there, where we have a P region, the collector region as a ring around a center emitter. We also have a buried layer underneath this whole device, and the purpose of the buried layer, well, once again, it's in there for resistance reasons, but it also is in there to kill the vertical substrate PNP transistor, and we talked about that previously also. But again, that vertical transistor would be from the P plus emitter going into the P base, then into the N epi, and finally into the P substrate. So there's your PNP transistor. It's not really drawn schematically on the drawing here, but there's a parasitic transistor that you really don't want turning on under normal conditions. Now the base region of this lateral PNP is basically the collector region of the vertical NPN, and it's the blue region, and you can see we have a base ring that goes all the way around the structure, and it's made up of N plus with sinker, and it contacts the buried layer down below. The actual transistor action is occurring right where I drew the transistor symbols. In that region, the base region is very lightly doped because it's made from the N minus epi material, so it is very lightly doped. However, that dimension is going to be much wider than a vertical device because it's difficult to get very small lateral dimensions as compared to vertical dimensions. So what this does is it generally leads to higher base resistance, which is the term RB, and a higher base collector capacitance than vertical devices. And you get a lot of base collector capacitance because you see you have a lot of base collector junction there. There's considerably more area of base collector junction than you have in a vertical device. That capacitance, that base collector capacitance, is often referred to as Miller capacitance, and it gets multiplied up by the beta of the transistor when the device is operating. So even a small Miller capacitor can look like a much larger capacitor because it gets gained up by the gain of the transistor. So the higher RB and the higher base collector capacitance tends to degrade the operating frequency range of this type of transistor. And this often is referred to as the unity gain bandwidth, or the FT of the transistor. The next cross-section I'd like to talk about is the CMOS transistor. And there's actually two flavors of the CMOS transistor represented on this picture here. We have the NMOS transistor on the left and the PMOS transistor on the right. The NMOS transistor has a N plus region for its source and drain with a P body, and the PMOS transistor has just the opposite. It has P plus source and drain with an N body. But aside from that, the two transistors are very similar to each other. They're just sort of opposite polarities. And I've drawn in schematically what they look like underneath each of the associated transistors there. There's actually a very thin oxide underneath the gate on each of these transistors. And that gate oxide is sort of the whole secret to MOS transistors. You needed a very thin gate oxide because these transistors use a field effect to create a channel underneath the gate connecting the source and drain together. So this is the basic theory of MOS, is that you use an electric field to create a conducting channel that shorts your source and drain together. I'm not going to get into great details on the theory of MOS. I'm going to talk about that in a later lecture, at least to some simplistic degree. I just really want to stick to the cross sections for this lecture. The gate oxide is much thinner than the other oxides on the chip, and if we look in between the contacts here, you can see some thicker oxide regions. That's often known as the field oxide, or LOCOS, which stands for local oxidation of silicon, or sometimes it's called STI, which stands for shallow trench isolation. The theory behind MOS devices, and we've just touched on that briefly, is much simpler than bipolar transistors. MOS devices are basically majority carrier devices where the electrons are conducted in N regions and the holes are conducted in P regions, as opposed to bipolar transistors where you're mainly a minority carrier device where you have electrons being conducted through a P region and holes being conducted through an N region, and that those regions are the base regions. However, for MOS devices, it took years for the industry to learn how to create the thin, reliable gate oxides needed to make MOS devices work. And because of that, bipolar transistors really took off during the early days of the semiconductor industry. Once MOS devices caught on and processing advancements came and made the gate oxides reliable, MOS transistors have now really dominated the market, and I'd say probably 90% of all the circuits manufactured today are MOS. There's still a market out there for bipolar, but MOS has really been dominating for a number of years now. Of course, there's some very desirable characteristics that you can get with a bipolar transistor that you just can't get with a MOS, and that's one of the reasons bipolar is still around. Another advantage MOS has over bipolar is no isolation regions are needed. Remember when we talked about the bipolar cross-sections, we had to put in isolation regions to isolate the collector of one transistor from the adjacent transistor. Here we don't need that. You can see we have an NMOS and a PMOS right in the same substrate with no isolation regions, and everybody's happy. We could add additional NMOS transistors or additional PMOS transistors with no isolation regions needed, and this allows CMOS to pack denser than bipolar. If we look at the NMOS transistor, you might notice that the body is tied to the substrate, and that contact is labeled sub. Now the substrate here is actually drawn as two separate regions. We have the P plus substrate, which is a highly doped P substrate on the bottom, and a P minus epi region on top. And you need to put the transistor in a low doped epi region because you need a low doped body region, but you really don't want the substrate to be low doped because that makes latch up very easy. And again, in a later lecture I'll talk about latch up concerns and why you want a high doped substrate to reduce latch up. But this is how you get that. You start out with a highly doped substrate, a P plus substrate, and you grow an epi region on top of that with low doped P, and then you put your NMOS and PMOS transistors into that epi region. For common digital circuits, the source and body of each transistor are shorted. Here, the source and body contact, both for the NMOS on the left and PMOS on the right, we have separate contacts for each one, so you could tie the source to a separate voltage than the body. But for most digital circuits, you don't need to do that. And in order to save room, you can remove the oxide that's separating the source and body contact, and you can just shove those two regions together and have a single contact going to both the source and body. It saves some room by doing that. And that type of contact is known as a budding contact or an integrated body tie, and it's very common to use that type of contact with digital circuitry. Now I'd like to talk about DMOS transistors. DMOS stands for Diffused Metal Oxide Semiconductor Transistor, and typically this device is made by diffusing a body region laterally under the gate. And if we take a look at the above drawing here, you can see that the P body has been diffused laterally or sideways underneath the poly gate. And that area where the P body is actually diffused under the poly gate is where the transistor forms. We have our source, N plus source, on the left. Then we have a P body underneath the gate. And then we have an N well connected to an N plus region that forms our drain. So it's an asymmetric device. It's not the same in both directions. But this type of arrangement can give you a very short channel length because that channel length is being determined by how far sideways the P body has diffused. And this concept can be used for creating power FETs. That's one of its purposes. In the early days, before you could photographically define, or photolithography was not as advanced, and you couldn't photographically define very small gate lengths, you could still create a small gate length by laterally diffusing one, as shown here. And this was used in the early days to make power FETs. Now, usually we use a DMOS structure similar to this to create devices with high drain-to-source breakdowns. Now, you don't get that high breakdown in both directions. You're only going to get a high drain-to-source breakdown, not a high breakdown in the other direction, source to drain. So basically, a DMOS device is commonly used when an IC requires a higher breakdown somewhere than the normal device. Other operating characteristics, such as the transconductance, which is often abbreviated GM, will be degraded with this type of geometry. The next cross-section is a JFET. JFET stands for Junction Field Effect Transistors. And this type of transistor is made by creating a channel that can be pinched off by depletion layers. And if we look above here, the actual channel we're talking about is the channel formed by the P base. You can see there's a source contact at the left side of the P base region and a drain contact at the right side of the P base region. There's an N+ region on top, which is called the top gate, and then the N-epi and N-buried layer region underneath the P base, which we call the bottom gate. Now, you might recognize these layers. These are all the standard layers used to form bipolar transistors. So a lot of times your bipolar process will have JFETs available because it's all the same type of layers. It's just mixing them up in different ways to get a different type of device. So normally the top gate, which is that N+ region right smack in the middle here, and the bottom gate, which is the N+ contact over to the right side of the N-epi region, are shorted together in metal. So they act as a single gate. And the drain to source conduction through that P base region gets modulated as you change the voltage on the top gate and the bottom gate. Now, what you're doing is you're applying a voltage to the gate that reverse biases the P base to gate diode, or P base to N+ or N-epi diode. When those diodes are reverse biased, they form a depletion region, and as you put more voltage across that depletion region, it grows and pinches into the P base region. So it gives makes the area that you can conduct through in the P base less. So this is a depletion mode device. The more gate voltage you apply, the less channel conduction you get. The actual gate current that you see here is much lower than the base current on a bipolar transistor. The gate current here is basically just the reverse bias leakage current of the diode, the channel to N+ or the channel to N- diodes. There's two diodes, one at the top of the channel and one at the bottom of the channel. And those leakage currents would sum together to give you a total gate current, but it's going to be much smaller than a bipolar, where you're actually providing the base current to some bipolar transistor. JFETs are generally used in low noise application. That's one of the nice things about JFETs. They're very low noise. Or another alternative would be where a low gate current device is needed, but you don't have MOS transistors available. Of course, MOS transistors are going to have an even lower gate current because they have an oxide insulator on the gate. So it prevents even the reverse bias leakage current of a diode that you see with the JFET. Now I'd like to talk about diffused resistors. And the drawing here shows a P+ resistor in a typical bipolar process. Now, simple resistors can be formed by placing two contacts into the same diffusion. And as you see up on top here, we have a P+ region in the middle of the drawing here, and we're contacting it at the one end with T1, terminal 1, and we're contacting it at the other end with T2, terminal 2. and the P plus region forms a resistor as drawn in schematically there. Now there's a third contact, often called the body contact, and that's provided for the material that the resistor is sitting in. In this particular case, the resistor is sitting in an N minus epi region, and you can see the body contact is the N plus contact at the far right of that body region. Now you can see there's going to be a diode formed, a P plus N minus epi. So what you would normally do is you'd normally take the body, and you don't want that diode ever forward bias. So you take the body and tie it, in this case, to a very high voltage, say the highest voltage on the chip, or you could tie it to one end of the resistor if the resistor is being used in a DC manner where one end of the resistor will always be at a higher voltage than the other end of the resistor. You would take the body and tie it to the end of the resistor that is at the higher voltage, and that would keep the P plus to NFE diode off when you're using this resistor. Just like a bipolar transistor, this resistor, this P plus resistor, needs to be isolated. And you can see we have isolation regions on the left side and the right side here. And that's because this is a bipolar process, and we really can't have the body of this resistor shorting to the collector of an adjacent device here. The N plus buried layer down underneath the resistor does more than just provide a low resistance path for the body. You don't really need much of a low resistance path there. There's not going to be much current flowing through the body contact. It should be just the current of a reverse bias diode. The N plus buried layer actually does something important here. It kills the vertical PNP beta of the parasitic device formed by the P plus NFE P substrate. What you do is you put the N plus buried layer in there, and that gives that parasitic PNP a very high dope base region, so there's going to be a lot of recombination in the base, so you've driven the beta very low on that device. Now often you'll use a silicide blocking mask with a resistor, and a lot of times diffusions will get what's called a silicide layer on top of them, and the silicide layer is a conducting metallic silicon compound that is formed on top of the resistor, and it can severely lower the resistivity of the region. That's great for making contacts, but for a resistor you want to get the resistance of the bulk material, in this case the P plus material. So you'd want to block that silicide at least over the body or the main part of the resistor here. Now diffused resistors will have a voltage coefficient, and that means that as you change the voltage across the resistor, or maybe move the two terminals up and down relative to the body, the resistance will change. You won't get, say you were measuring this on a curve tracer, it might not look exactly like a straight line. At low voltages it would look pretty much like a nice straight line on a curve tracer, but as you got to higher voltages you might see it start to bend a little bit. And that's a voltage coefficient. And that voltage coefficient is being caused by the depletion region between the P plus and the NEPI region. And this is similar to what we see in a JFET. As we apply more reverse bias across the P plus and NEPI diode, some of that depletion region is going to eat into the P plus region and change its value. Now in this case, the P plus is much higher doped than the NEPI. So most of the depletion region will move into the EPI, and very little of it will move up into the P plus region. So a P plus resistor probably won't have a large volt co, but it will have some, and you'll see that with all types of diffused resistors. If this was an N minus resistor or a P minus resistor, you'd probably see more of a Voltco because it's a lower doped material. Now I'd like to talk about pinched resistors, and the picture here shows a pinched P-base resistor in a typical bipolar process. Now there's lots of ways to make a pinched resistor, and this is just one of the more common ways, and this is the only one I'm going to show, but I wanted you to understand what a pinched resistor looks like and the basic concept behind it. Pinch resistors are sometimes used when a large value of resistance is needed. And a pinch resistor is formed when one type of diffusion, in this case P-base, is pinched by two other types. And it's being pinched on top by an N+ region and on the bottom by an N- epi region. And if this looks familiar, it should be, because this looks exactly like that JFET structure we saw earlier. The only difference is there's really no signal placed on the gates in this one. The gates would be tied to some DC voltage somewhere. The resistance value, again, is the resistance from a terminal T1 to T2, and that's the resistance of the P-base region. But that resistance is being pinched both from on top and on the bottom by depletion regions, and you could be tying the body regions to a supply to get a lot of reverse bias on those diodes and really pinching that channel. So the resistivity of the channel, the P-base channel, could be very high. This type of structure can provide a large but not well controlled resistance value in a very small area. So if you really need a lot of resistance in a very small area, and you don't really care how well controlled it is, this would be a good option for you to consider. Well, one thing to consider is the dual depletion regions do cause the resistor to have a very large Voltco. So the resistance is going to change a lot as you apply a voltage to and from this resistor. The next device I'd like to talk about is the polysilicon resistor. And the drawing here has a polysilicon resistor shown in a typical CMOS process. The actual resistance is shown sort of in the upper middle part of this diagram, where we have a sheet of polysilicon and some contacts opened at the left side and the right side. The heads of the polysilicon resistor usually are silicided, meaning there's and we talked about silicide before, a metallic silicon compound that is on the surface to give a good contact resistance. But then the body of the polysilicon resistor, you're going to want to block the silicide in that area so that you can get a fairly high sheet row or sheet resistivity of poly in that area. Generally, polysilicon resistors are completely surrounded on all sides by insulators, such as silicon dioxide, and therefore the capacitance of this type of resistor is fairly low because you don't have any junction capacitance to deal with here. Since there aren't any depletion regions, because there aren't any junctions, polysilicon resistors also generally have low voltage coefficients. If the polysilicon is completely covered in silicide, you could have a resistivity somewhere around 5 ohms per square, which is pretty low. If you have a lightly doped poly and the silicide is blocked, the sheet row could be very high, several kilo ohms per square. So there's a whole range of resistors you can make out of polysilicon, and they're very, very useful in many cases. Next, I'd like to talk about thin film resistors. And the drawing here shows a typical thin film resistor in a bipolar process. Thin film resistors are made from a thin conductive layer placed underneath the metal one. And as shown here, that conductive layer might be made out of a nichrome film or a cychrome film. There might be other ones, but these are pretty common. The typical film thickness is somewhere around 10 nanometers versus 800 nanometers for metal 1. So you can see the drawing here is way off scale. That metal 1 that I show sitting on top of the thin film would roughly be 80 times the thickness of the thin film. That's why it's called thin film. Thin film resistors have very low capacitance and low voltage coefficients because they're basically a metallic resistor. The film composition can also be tailored to have a very low temperature coefficient, which is often useful for building temperature compensated circuits, maybe like a band gap circuit, where you want a very low tempco resistor. Now, depending on the material used, the sheet row or ohms per square of the thin film can vary from maybe 100 ohms per square up to several kilo ohms per square, again depending on the type of material used to construct the thin film. One of the nice things about thin film is they can be laser trimmed to achieve very precise values, and this ability to trim the resistor can be very useful when producing precision analog circuits. If you're building an op-amp, you could come up with a circuit where you could trim the thin film resistors to dial in the offset voltage. So you could trim out the offset voltage to get it a very small value. The next device is the basic PN diode, and there's a ton of PN diodes out there you can build. This just shows how to build a couple of them. This is the P-base N collector diode in a typical bipolar process. You can also see the P substrate and epi diode, both of which are indicated on there with the diode symbol. Most processes have multiple PN diodes available. Bipolar processes have base emitter diodes, base collector diodes, and substrate diodes. So there's a lot of diodes out there. You also have just substrate to N minus or P-iso to N minus. MOS processes have source body, drain body, and body substrate diodes. And now a substrate diode is a diode where one of the terminals is hardwired to the substrate. And if we look at the bottom diode in the above diagram here, you can see that its one terminal is tied to the substrate, so that terminal can't be tied elsewhere. Whereas the upper diode in the picture, the P-base N minus epi, those terminals can both be tied to different places, so you're not tied into a substrate anywhere. Diodes made from different diffusions will have different leakage currents, different capacitance, and different breakdown voltage characteristics. And I'm just going to leave it at that. I'm not going to go into that in great detail. Just be aware that not all diodes are equal. There's quite a bit of difference in capacitance, leakage, and breakdown voltage depending on the doping level and the size of the junction. The next device type is the Schottky diode. And the drawing here shows a Schottky diode in a typical bipolar process. Schottky diodes are made when metal comes in contact with N- or low-doped N material. And that's what we're showing in the middle of the drawing near the top here, where we have a metal 1, which could be platinum or titanium, coming in contact with an N- epi or collector region of a bipolar. And that actually forms a Schottky diode, and you can see I've placed the Schottky diode symbol on that junction right there where the metal contacts the N- epi. Now the metal in this case is actually acting as the P side of the junction. Now these junctions often tend to be a little bit leaky, mainly right at the corners or at the edges. So you often put guard rings of P diffusion around the outside of the Schottky diode to reduce the leakage current. And that's what those P plus regions on the left side and the right side of the Schottky diode are. Those are the guard ring regions, and that would be a ring all the way around the diode. Now the guard ring creates a PN diode that's in parallel to the Schottky diode, and you can see I've drawn in the PN diode, and yes, it is actually in parallel with the Schottky diode. However, the Schottky diode will typically have a much lower forward turn-on voltage than the PN diode. The forward turn-on voltage of a Schottky diode might be somewhere in the range of 0.2 to 0.5 volts, depending on the metal used for the P region, and that would compare to something in the range of maybe 0.7 volts for the normal PN diode. So basically the Schottky diode is going to turn on first before the PN diode. Schottky diodes have low capacitance because there's not much of a depletion region here. You're going right up against metal, and they have very fast turn on and turn off times. Now I'd like to talk about a Schottky transistor, and with this topic I guess I'm really dating myself. I don't know if anyone even builds Schottky transistors anymore, but I wanted to discuss it just to show you that it was a pretty neat idea at the time. Schottky transistors were used in the 1970s and 1980s to make Schottky TTL circuits. And it's basically you're taking a bipolar transistor, and you can see the bipolar transistor here. It's an NPN transistor, and you're opening up the base collector contact and letting the base metal touch the collector region. And as we just talked about the Schottky diode, anytime you have metal touching a low-doped N region, it'll form a Schottky diode. And the schematic of what you get is over on the right-hand side of the drawing here, and you can see we have a bipolar transistor, and then we have a Schottky diode basically in parallel to the base collector junction. Now the Schottky diode will prevent the transistor from going into deep saturation. If you try to saturate this transistor, which basically would be forward biasing the base collector junction, the Schottky diode would forward bias first and prevent a lot of the charge being stored in that base collector junction. And what that means is that when it came time for the transistor to come out of saturation, it could come out much easier or much faster because you didn't have all that diffusion capacitance of the base collector junction that you had to discharge. Next, I'd like to talk about Zener diodes. The picture here is a buried Zener from a dual well CMOS process. Zener diodes are constructed by placing P+ region up against an N+ region and forming a high dope junction. Now the high doping in this junction will typically cause the diode to have a reverse breakdown voltage in the 5 to 7 volt range. In a buried Zener, the P+ N+ junction is formed vertically below the surface. And if we look at the picture above here, just where I've drawn the schematic symbol, you can see the N+ region is touching a P+ region just below it, and that forms the buried Zener. Now you can also make a surface Zener diode. Now I don't show one in the picture here, but if you just picture taking a P+ region at the surface and having it touch an N+ region at the surface laterally, that's basically how you'd make a surface Zener diode. However, buried Zeners will generally be more reliable and have a much more stable breakdown voltage over time than a surface Zener. So generally, if you need reliability, a buried Zener is the way to go. Now the device engineers tell me that a low tempco on the breakdown voltage can be achieved by balancing avalanche versus tunneling conduction, and that's done by changing the relative dopant levels of the N+ and P+ regions. If this is done just right, you'll achieve a breakdown voltage somewhere in the 5.1 to 5.4 volts, and it will be very stable over a wide range of operating temperatures, and that's very nice from a circuit design standpoint. This next device is a MIM capacitor. Now MIM stands for metal insulator metal, and this type of capacitor is a parallel plate capacitor. One plate is made from one of the standard metal layers, and the other plate is generally a dedicated metal layer used exclusively for the capacitor. And if we look at the above drawing here, you can see that the lower plate of the capacitor is made out of metal 1. That would be one of the standard metal layers in the process. But the upper plate here is made out of a layer called CTM, which stands for capacitor top metal. Now that layer is only used for capacitors. You won't find that anywhere else in the circuit. It's not used for interconnect or anything. It's in there specifically for capacitors. And you make contact to it by coming down from metal 2 through a couple of vias to actually contact the capacitor top plate, as shown in the drawing there. Sometimes a higher metal is used for the bottom plate to reduce the substrate capacitance. And what I mean by a higher level of metal, here we have the capacitor bottom plate on metal 1. Well, that's pretty close to the substrate, so you're going to get some parasitic substrate capacitance. Let's say you took this whole structure and moved it up to a higher level of metal. Instead of using metal 1 and 2 here, you used metals 3 and 4. Well, this whole structure would be higher off the substrate, and that would reduce the parasitic substrate capacitance on the bottom plate of the capacitor. The dielectric used between the two plates here is not your standard dielectric. It's usually something other than silicon dioxide, maybe silicon nitride, something that will give you a higher capacitance per area. In addition, it's very thin, so that also adds to the capacitance per area. So you can get a lot of capacitance out of a structure like this. The MIM capacitors have high Qs, or quality factors, and they're ideal in many applications. Now, a quality factor in this case would be the ratio of capacitance to resistance. So you'd like a lot of capacitance with very little resistance, and this type of capacitor does that very well. Now, we did say that the dielectrics are very, very thin, and because of that, this type of capacitor generally cannot withstand high voltage. So if you need a high voltage cap, you're going to have to use something else other than a MIM capacitor. MIM capacitors require extra masking steps to put this capacitor top metal in there, and generally those are optional, so you can choose to have those or not. So if you want a MIM capacitor in your design, you generally are going to have to pay extra for the extra processing steps needed to put one in there. The next type of capacitor I'd like to talk about is called a finger capacitor. And a finger capacitor is made by interleaving metal and poly layers in an overlapping structure as shown above in the drawing here. Once again, it's a type of parallel plate capacitor, and it has a low voltco, and it has a very good Q because it's all metal and it's a parallel plate. There's no junction involved anywhere. The total capacitance is the sum of several vertical and lateral capacitors in parallel. If you look at the above drawing, you can see that I've drawn in a bunch of capacitor schematic symbols in here. Some of them are vertical and some of them are lateral capacitors. The dielectric between the plates of the capacitors is the normal ILD, which stands for interlayer dielectric, and because of that it's fairly thick. Now, this thick dielectric reduces the capacitance per area that you get out of this structure, so you're probably not going to get as much capacitance per area as a MIM cap. However, you are stacking it up, 3 or 4 layers here, so you're trying to concentrate the capacitance, but you still probably aren't going to get as much as a MIM capacitor in the same area. However, this type of capacitor does operate at fairly high voltages because you're using the standard interlayer dielectric as your dielectric between the metal plates. Another advantage finger caps have is they don't require any extra masking steps. This uses all the standard metal layers and all the standard interlayer dielectrics. So there's no additional cost for using a finger cap, well, aside from the extra area that it takes up. The last device I'd like to talk about today is an on-chip inductor. And it is possible to make an on-chip inductor by spiraling metal layers. And if we look at the cross-section up on top here, it's kind of hard to tell what's going on. But if you look to the right here, I've drawn in a top view. And you can see that we're actually taking a piece of metal and making a spiral out of it and making contact to it at both ends of the spiral. Now the inductive coupling is caused by current flowing in the same direction in adjacent legs of the spiral. You can see I've drawn some arrows on the spiral here to indicate the direction of current flow, and you can see some adjacent legs there. The currents are actually flowing parallel to each other, so you will get some magnetic coupling between those legs. The typical value of this type of inductor is just a few nanohenries, and because of that, it pretty much limits their use to RF frequencies, probably 2 gigahertz or greater. Now, you generally will use the thickest layer of metal available to build these inductors, and that's usually the top layer. And you do that to get a better Q, or quality factor. And again, quality factor in this case would be the ratio of inductance to resistance. You'd like all inductance and very little resistance. And that's why you want to use a very thick metal layer, because very low resistance. Also, by putting an inductor up at the top metal layer, you've reduced the parasitic substrate capacitance, because that top layer of metal is further off the substrate. Now the quality factor, or Q, can be improved by using an octagon structure or even a circular type spiral, and it's called an Archimedes spiral, instead of this squared off spiral that I'm showing here. You get a lot of extra resistance in this type of spiral in the corners, and you don't get the inductance in those corners. So by using one of these other structures, you can improve your Q. Ground shields can also be used to improve the Q, and a ground shield will prevent some of the losses due to eddy currents in the substrate. And you can see I've drawn a ground shield on the cross section down below. And generally these things are made out of poly, and they're broken up into radial slices. And the radial slices will tend to reduce the eddy currents. The eddy current in the substrate won't be able to follow the spiral inductor above. It'll have to flow through the radial slices.
Conclusions. I hope this talk has expanded your understanding of what integrated circuit devices can look like. However, this industry is rapidly changing, and devices are constantly being improved and modified. The majority of devices being fabricated today are much more complex than the simple cross-sections I've shown in this talk. However, many of the concepts I presented here are still in use. Thank you for your attention.